Hello, today I'll be talking to you about machine learning in the study of star clusters with Gaia EDR3. This is work that has been done with some of my students and collaborators mentioned over here. Now, the importance of studying star clusters is very well known because star clusters are the basic building blocks of galaxies, and they're required to understand the formation of evolution of galaxies, and it's important to study stellar cluster populations, etc. But one of the biggest problems in star cluster studies is the problem of membership. Now, we know the spatial location of the members, but identifying them was earlier done essentially using the color magnitude diagram, but now it can also be done using the vector point diagram, the parallax proper motion diagrams, etc. So the wish list, if we want to actually find members of a cluster, that is stars which are born from the same molecular cloud, they should have the same velocity, they should have the same distance, and therefore what we need is high precision astrometric data, positions, parallax, and proper motions, and they are the ones which would be used to actually find out members. And the wish list comes true with the event of Gaia, which gives us unprecedented astrometric data with which we can actually get information for 1 billion stars in our galaxy. Now, Gaia basically has two identical 3-meter astrometric telescopes. And basically what it does is it gives you an accuracy of about 24 microarc seconds to a distance of about 45 kpc with very good accuracy. It can be used for galactic archaeology, and it has been giving us really good insights into the structure of our galaxy. Now, machine learning comes out to help in such cases because it actually helps us in doing object identification, classification, cleaning images, making schedules, making simulations go faster. In this case, what we do is you could be using supervised methods or unsupervised methods as well as reinforcement. So today I'm going to talk about some supervised as well as unsupervised methods which are being used for membership determination. So I start off with the paper which we did about 2 years ago, which was a membership of star clusters using a random forest with Gaia DR2. And what we basically used in this is we used membership data from another paper, which was Candet-Gordon 2018. That was used as the training set. And then we used random forest, which is a supervised classification method to find out the other members. So we had a sample of 9 open clusters, which had a variable age from 1.3 to 20 million years, galactic distance ranging from 7.3 to 14.5, and varied galactic latitudes and longitudes. So here we have our data set, which was derived from this paper. And from this, we had the basic parameters as well as individual stars with their membership data. So what they had used was a method called upmask, where they start off with the photometric data and the clustering algorithms to actually get cluster members. Now, using this, we actually got proper motion and parallax plots for our 9 clusters. So what you see in this, the orange plots are the Candet-Gordon stars, which are the training data set, and the blue ones are the ones that we derived using random forest. Now, the Candet-Gordon paper took it from a very restricted small area. We looked in a larger area, so we identified members which are more in the outskirts of clusters also, which you can see in all our 9 clusters. But here you can see the plot in terms of parallax. You have orange for their set, blue for ours, and green for the combined. So you can see in the combined data set, we quite agree with the original distribution which was given by Candet-Gordon. Blue ones are only our stars, excluding those stars. Similarly, if you see in proper motion data, you can see that there are certain lumps in velocity space. That's the Candet-Gordon data. These are the additional stars by us, and this is the combined data of Candet-Gordon as well as ours. So you can see that we can now see substructure in our velocity space because of the addition of our things for our 9 clusters. Sky plots also show us a lot of other structure. You see some of them show further clumps which are visible for the clusters using our data set. And the color magnitude diagrams you can see are visibly enriched. Orange ones were the original ones, and then the blue ones are the ones which we added using our data. So you can see that we can very well see these additional stars which were not noticeable in the earlier case. We validated this by dividing the training set in the ratio of 30 to 70 to actually look what was our retrieval rate of these things. And with that, we actually have a retrieval rate, and we define the precision to this. This is the ratio of our members to the Candet-Gordon members, where we've enriched it by 2 or 3 times. And in that way, we are improving the sample which can be used to find out cluster parameters and other important things. So the results, it actually gives us very good enriched membership as well as a better data and substructure in velocity space as well as in in the sky and in the color magnitude diagram. After this, we tried out an experiment. What if we use supervised? This was using supervised learning methods. The pros is that it performs better, But it obviously depends upon the accuracy of your training set. So let us assume that we, if you're not so confident about the training set, how could we use unsupervised learning methods? So unsupervised learning methods, the training set is from the raw data. You actually look for clusters or samples within the data to define the clusters which you have. So there are different clustering algorithms which could be used. You could use centroid based, which is k-means, connectivity based, density based, and distribution based. So we explored basically these two ones. One is the density based, which is the DB scan method, as well as the GMM method, which is the Gaussian mixture models. So we try to test whether does it work for all clusters or for different field cluster ratios. It has been explored by earlier authors, Gao 2018 as well as Agarwal 2020, and they have used Gaussian mixture model to look for membership. What Gaussian mixture model basically does is if it looks at a sample of stars, it basically looks for two clusters. So you'd get them in form of Gaussians, you break it up, right? But in this case, obviously, this is the earlier paper by Manan and Agarwal, which they used for looking for Gaussian mixture model. Now we did it for a larger sample. We did a sample for 10 stars for which we actually look for this. And using Gaussian mixture model, you can see that in some of them we have an improvement in the membership of candidate Gordon, but in some of them it's not necessarily always a membership improvement. It is not always like that. So here you can see the sample data for IC1805, where you can see that the GMM members are marked in green, the candidate ones are marked over here in purple, and the orange ones are the ones which we have, the non-members. So you can certainly see that there's a separation. So you can see here, these are our members, these are the non-members. The members show a peak, while the non-members are more spread out. Here are the members, non-members. Here you can see it in the sky plot. You can see it in the terms of the velocity plots as well as the color magnitude diagrams. So what we did is we actually defined a modified silhouette score, which was the difference of the standard deviations for members and fields divided by the maximum to actually look for how well our method is working. We plotted our MSS versus the distance, and we found that the only thing that seems to correlate is that it works better for closer clusters. And with other parameters, we find a very weak correlation for the GMM performance. So that's not a very good indicator of whether GMM works. Now to couple this, we also use the DB scan method, where you look for a point and you look for the neighbor around it, and you look for if it has the minimum, you look for the epsilon radius, you look for the minimum number of members. If it falls within that, it is a cluster. If there is a star for which the neighborhood does not have the minimum amount of points, it could be a core point or it could be a noise point if it does not have those amount of members, or it could be a border point. So using that, we actually try to look for clusters, and we use this is a paper which is going to be submitted very soon, and we had our members from DBScan. We compared it to our random forest members and the candidate members to actually show how well we do it. And what we see is that membership gets increased by a factor almost 4 times. It improves the accuracy in determining parameters. Sizes are also increased, and we have not, since we don't use photometric membership, we actually can look for variable stars in the color magnitude diagram, which would otherwise not be explored. Right, so you see the candidate Gordon, the purple ones, you see them sitting over here, but using random forest as well as our method, we are identifying these pre-main sequence stars, which are also members. So we ran Azteca, which is a code to actually find out stellar parameters, and compared it to the values which we got using candidate member, and we actually got these kind of values for our stars. Again, a sample of 9 star clusters for which we are getting candidate members, random forest, as well as the DBScan members. So what we saw is, like I said, the numbers increased very largely, and we get much better accuracy in our color magnitude diagram. So the future shows that machine learning members are gaining popularity, especially in this case for this thing. Further exploration of methods and their potential are very essential to avoid a black boxy approach, and that's what we basically be doing in terms of comparing different methods of membership to find out machine learning methods to find out membership for star clusters. And thank you very much.